Hello everyone. Today I want to talk about universal classical quantum multiple access channel coding. My name is Masahito Hayashi, and this is joint work with Ninchai from Shanghai Tech University. This is the content. In this talk, firstly, I will explain the formulation of classical quantum multiple access channel. Then later, I will explain our result. This is the formulation of classical quantum multiple access channel. Circuit MAC is defined with two classical inputs, A and B, and output, quantum output. This quantum output depends on the input classical symbol A and B. Then our code is defined by this way, but in this case, we consider joint decoding. So encoder is defined by a map from message to alphabet. So J to A, and we have a two encoder. This is Alice's side encoder, and this is Bob's side encoder. And we have a decoder. Decoder is P of M on this output system, and this P of M will recover two messages J and K. In this case, we have decoding error probability in this way. So this is our decoding error probability. This is capacity region. So this is capacity region. So our capacity region is defined by the pair of transmission rate with reliable transmission, and this one is defined and calculated by Andres Winter. So we have this formula. So this is Alice's transmission rate, and this is Bob's transmission rate. And this transmission rate is characterized by this way. And here we take union because we can optimize the choice of input distribution and P and A. This is product distribution. This capacity region can be attained by applying the time sharing and achievability of corner points. So what is the corner point? Corner point is this one. So for example, capacity region is displayed in this way. In that case, this point and this point is corner point. And Andres Winter shows that the achievability of corner points, and he applied time sharing. Then we can achieve the, this point, this general point. This is our result. In our setting, we consider a set of our channel W, and we don't know which channel is true channel. So in that case, we need to construct a universal code. In that universal code, we can achieve this corner point. So here is a corner point, and we consider a minimum value of this one and this one. So we consider minimum value for the respect each corner point, and we take convex file by using the time sharing. So we can achieve this red region by simple method combination of the time sharing and the universal achievable code for the corner point. This in this code, essentially encoder is constructed by generalized packing lemma, and the decoder is constructed by using sure duality. But we have some improvement. So we can consider separate decoding. So separate decoding is different. So encoder is same, but in the decoder side, we consider two P of M, two decoder P of M. Each decoder POV recover only one message. So this is Alice's decoder, and this is Bob's decoder for the Bob's message. So we consider two decoder in this way. So then we define decoding error probability, two kinds of decoding error probability. Of course, in the realistic situation, we can apply only one decoder, but theoretically, it is very important to consider this problem setting. So we have this result. If we allow that kind of separate decoding, in that case, we can achieve this transmission rate universally. So we have a universal encoder and a universal decoder with separate decoding to attain this capacity region. So here we minimize this mutual conditional mutual information. We have this capacity region, but this capacity region is strictly larger than this previous achievable region. So there exists an example such that this inclusion is strict. However, we have a good idea because there is a good method to convert separate code with separate decoding to code with joint decoding. So using this conversion, we have a good code with decoder with joint decoding to satisfy this inequality. So in that case, if each decoding error of separate decoding go to 0, then this decoding error probability of joint decoding go to 0. So using this conversion, we can show that this capacity region can be achieved even in the universal setting. So we can achieve this capacity region. Finally, I want to explain our example. So this is a classical example, but we can consider a similar example even in the quantum setting. So in this example, we have a two input case, A and B. Both input is binary information, and we have two channels. So then we have a W composed on the two output, W0 and Y0 and Y1. And first one is simple modulo sum, and the second one is somehow different noise. So in that case, first channel and the second channel is different output. So anyway, so we have this one and this noise. So in that case, our universal code can achieve in this way, this point, this red region. However, if we can achieve only the corner points and its time sharing, in that case, our achievable rate region is this one. So this is the conclusion. We have shown CQ universal Mach code with joint decoding by modifying the universal Mach code with separate decoding and shear duality and general packing lemma. The key point of our method is conversion from separate decoder to joint decoder. This is the key point. And showing an example, we have shown that time sharing does not work in this problem. In this problem means that universal code. So this is the reference. Thank you very much.